maybe not. Hopefully still recording. Okay. Um, so today we're going to talk about something that I think it might be very familiar to those of you who are coming from computer science classes, because this is something that's covered extremely heavily in like an intro algorithms course, but we're going to try to talk about it maybe more in the context of some of the algorithms we've already seen. And this is trying to estimate the runtime and memory complexity of an algorithm. And I like to do this at this point in the course because we talk about this a little bit on the first homework, right? For example, when you simulate this toppling sand pile, one way to think about it is going to be breadth first or depth first simulations, and they end up being the same because it's an abelian group. But this is actually going to come up quite a bit when we talk about numerical linear algebra, because numerical linear algebra is a bunch of very, very similar algorithms that are really differentiated by the fact that they get these small shave-offs in the runtime. So it's useful for understanding that. It also is very useful for understanding why numerical integration is the way it is. There's this whole family of algorithms out there that are basically trade-offs between precision and runtime. So it's very useful for thinking about that. And maybe on a more practical note, those of you, the 65% of you guys that are considering getting jobs in tech, these are like a very common thing you're asked to do during interviews is what is the runtime complexity? It's like a classic question. So it's useful to see a little bit of this and then see a lot more of it later. So we're going to talk about this, and we're going to do this actually in the context. I've modified this lecture a bit because I wanted to tie it to what we saw before. So we're going to talk about this in the context of something we saw before in the last class. Okay, so in the class before the last. Okay, so we talked a little bit when we did object-oriented programming about the logistic map, which is this one parameter dynamical system that exhibits this behavior where as I sort of iterate that map over time, it goes from exhibiting limit cycles to slightly longer limit cycles. And then as some parameter of the map gets really big, it exhibits a fully developed chaos. So we're going to use some of these algorithms or some of these methods we'll see today to see if we can isolate those points where those bifurcations occur. And then we're going to get a surprisingly good estimate of something called the Feigenbaum constant using some of these algorithms. Okay, so the first thing I want to do is I want to implement the logistic map again because I want to have it in my memory. So I'm going to do this a little bit differently than we did it last time. So last time you recall I defined a dynamical system class and I inherited from it. Here, because I'm just going to work with this one, I just straight implemented the logistic map. And if you're new to Python, it might be interesting to go through my code here because the way I've implemented this uses something that we haven't used that much before, which is I'm going to make heavy use of double underscore methods. So these are methods on Python objects that are treated specially by the interpreter. So the one that we've seen before is the init method, which is basically your constructor. And double underscore methods that have these special names, they tell Python to treat them differently. So for example, if Python sees something called double underscore init, then it knows that whenever you instantiate the object to run that method, even if you don't explicitly say that. So this one we've seen before, but it turns out that there are others. So I'm going to implement the logistic map using a couple of these double underscore methods just to see, so we can see how they work in context. So one of them is the string method. Some of you guys might use the representation method, which is very similar. So if you have a method called string, it basically tells print what to do. So if I print my object, it'll just run that method implicitly. Another one is call, which I'll see in context below. And this allows you to treat your function like an object. And then I won't get into this, but we'll also use an example of an iterable method, which makes your object act like something you can iterate over, which can be fun if used carefully. So my logistic map implementation is very similar to before. I've just put it all in one body. So I'm going to have the parameter that defines the map. I'm going to have initial condition. I'm going to set those as variables associated with the object. I'm going to define a next method. So this is similar to our one-step method. This actually implements the logic of the logistic map. So I take my current value and multiply it by 1 minus itself and scale it by the growth rate. And you'll recall that this number is this parameter that determines the bifurcation. My simulate method just runs that a bunch of times so I can make long trajectories. And then the two new things here is I'm going to have a call method. So this is just going to run this next method. But because it has a special name, it's going to allow me to use this method behind the scenes, even without specifically invoking next. And then I'm going to have a string method. So whenever I just say print my object, it's going to run this. So these are two double underscore methods that sort of allow you to.
What do you mean behind the scenes? Like
So I'm never going to actually call this method. So you'll never see me do something like map dot string like I would if I were doing something like map dot next. So you'll see me sometimes do this because it's a method bound to the object, but you'll never actually see me call this, even though it's technically a method. Instead, Python's going to use it when I call something, and we'll see an example of that downstream. Okay. Yeah. Okay, so that's my logistic map class. And before I do my bifurcation diagram class, let's just see what my logistic map class does. So I'm going to comment this out. I don't think I use it. Okay, so I'm going to instantiate the object. So now I have one example of this in memory. So the first thing I'm going to do is I'm going to try to print that object. So let's just run this. Okay, so that print method, when I call print on that, Python says, hey, he's printing this weird object he defined. It goes and it finds this method called string. That's probably what he wants. Then it just runs this logic. And this basically tells me to print out this, and then it calls the names of the two parameters. And so I get this nice little thing that says, this is your logistic map. So this just allows me to use print with this, which is kind of nice. And behind the scenes, built-ins that you print have a method like this. And then the other thing I'm doing here that is kind of, I don't know, unique, I guess, is that, so I set an initial condition when I instantiate the map. Instead of having to call map.next, if I just call map, even though map is an object, if I call it using a function syntax, so I just call it with that, this actually runs the next method, so I can get the first iteration just by calling the object like a method. And the reason that works is because I have this call that allows me to treat the function like an object. And this is something we're not going to worry about too much today, but when we do numerical integration, sometimes we'll implement ODEs as callable objects. So if you have some crazy simulation, you'll wrap all of your variables into that object, but then you might just call that object to simulate your system. Okay. And then this isn't so exciting, so I won't get into it that much. So my bifurcation diagram is going to be a class that implements this really sort of tedious work of iterating over a bunch of different parameter values, simulating a trajectory, seeing everything it does, and then plotting it. And I'm going to use some tricks behind the scenes to do this in a way that is a little bit more memory efficient. So I'm going to treat this as an iterable, where I can actually iterate over the parameter values using sort of this structure in Python that allows you to treat objects as if they were lists or something. And I won't get into the syntax on that, but if you are interested in Python, this is something to read a little bit about, is how to use iter and next methods. But here, for our purposes, this is just going to be a way that allows me to save a little bit of memory. Okay, but all that this class is going to do is just the same thing we saw last class, which is it's just going to run the logistic map a bunch of times for a bunch of parameter values and plot what happens. Okay, so I think this is all in memory. So, that's my logistic map in the chaotic regime because it defaults to 3.8 as R. Okay, and so then my bifurcation diagram class actually runs super fast. I think I can rerun it. Yeah, it takes about 1 second. And this is, I think, about 100,000 points on that plot. So it's super fast. So we saw this before, and the one structure I pointed out last time is that we're sweeping R here, and every one of these points, right, we have a super long trajectory associated with it. It's just that the trajectory doesn't do anything here. It goes to a fixed point, so we're plotting 1,000 points on top of each other. We start getting limit cycles here, so we start to get the 2 values, then we get 4, and eventually we get the crazy chaos here. And this gap here, someone asked me about it last time. So this is apparently a very famous result for the logistic map, which is that you get a period 3 limit cycle just out of nowhere in the chaotic regime. And there's some very interesting theory behind that. Okay, so this is bifurcation of the logistic map again, and it has this nice structure where it branches out. Okay, so I referenced this last class, but one thing that was very interesting to physicists interested in this, and actually ends up being sort of very conserved across a bunch of different dynamical systems, is what precisely are the values of R at which you get this splitting, right? Because it looks like maybe R is 3 here, so maybe that's your first bifurcation. Maybe R is like, I don't know, 3.45 here or something. But it'd be nice to know these values a little bit more exactly. So in order to do this, we're going to see an example of where you can really speed up an algorithm by using some very strategic structure. Okay, so if I just wanted to find these values sort of naively, the most obvious thing that you could imagine doing would be to just basically take the bifurcation diagram and detect these points manually. So I'm going to call this a line scan or a line search. And the idea here is that I'm going to take this bifurcation diagram and I'm going to just check every value of R and see if it doubled. I'm going to try to define that point just use it by evaluating this map a bunch of times. And this is pretty fast, but it's actually not the fastest way of doing this. So my line scan function is going to take a bunch of values of R. For every one of those values of R, it's going to simulate the logistic map. And then it's going to check a condition to see if the period doubled. And so this is basically doing the same calculation as my bifurcation diagram calculation. It just has this additional condition where it only stores R if it thinks it saw a doubling. Okay, so my actual condition I check, and this isn't the most interesting, this is just what happens to work for this, is for every value of R, it's going to check the trajectory that it gets, and it's going to compare that to the previous trajectory to see if the number of unique symbols is higher. The idea being that if I have something like a period 2 orbit, so that looks like this over time, that's n. A period 4 orbit looks something like, and so instead of having 2 unique states, it has 4 unique states. So all that this code does is it says, compared to the previous value of R, do I count 4 unique symbols instead of 2 unique symbols? And if you want to get really fancy, there's a way to do this using hashes. That's maybe a little bit more elegant, but you can also just count how many unique things you saw, and it's close enough for our purposes. So this is the condition I have to check, and if this condition fires a true, then it's going to say, okay, it looks like it doubled, and then you should count that as one of these special bifurcation points. Okay, so that is basically just going to run the logistic map a bunch of times. So let's go ahead and run this and see if it's still working. Okay, it looks like it is. And so in a relatively fast amount of time, it checks all of these different values of R. So it scans a really, really dense range of them, and it finds these special points, or it finds its best estimate of these. And it looks like it found these points as equal to 3, 3.4, 3.5, 3. It looks like it's a little bit, I guess it's around 3.44 there, so that's close enough. So it gets these relatively accurately. Okay, so 2 questions would be what sets the precision limit on this, and then how long does this take? So the precision limit is pretty easy to guess, which is that if I'm doing a line scan with 300 values checked, I'm only going to get a precision of 1 over 300. So the precision of my estimate is going to be bounded by how many points I check in this interval. That's important because that means that if I want to get a really, really high accuracy estimate to, I don't know, five significant figures, I have to massively increase linearly the number of points that I'm checking. And this gets into the real limitation of doing a line scan, which is that the time that it takes to calculate this quantity is directly proportional to the number of R values I test. And the reason for that is because for every single value of R, I have to run a simulation logistic map. And it's not that slow on my computer, but it still is a lot of compute behind the scenes. And so in principle, there might be ways to avoid having to do all of this compute, especially given that once I'm in this region, I kind of don't do anything until I get to here. So there's some intuition to believe that there might be a way to do this faster than just checking every point in the bifurcation diagram. Okay. Oh yeah, and here I just overlay the values so you can sort of see where they are relative, and they're actually pretty close to the doublings. Okay. So before we get into how to get this faster, one of the things I'm very interested in is I talked about how there's some universal structure in the ratio of this distance to this distance to this distance. So this is extremely hard to see on a simulation that I can do on my laptop, but I think I actually got surprisingly close. So we'll see how I do. Okay, so here what I'm going to do is I'm going to take the gap between these critical values. So this distance to this distance, I'm going to call a gap. This distance to this distance. And you'll recall that I seem to think that there might be some pattern in the rate at which this distance is decreasing as these doublings come on. Okay. So here I ran that code. I had a bunch of values of R. I find the gaps between successive values of the bifurcation number. And here I'm just going to plot the ratio to see what that factor of decrease from here to here and here to here, as if it was a geometric series, like a bouncing ball or something. And it looks like I got pretty close. So I got that my first gap decreased by about a factor of 1 over 4.6. And then here to here looks like it decreased by a factor of about 1 over 5. So that's interesting that those numbers are very close to each other because it suggests that maybe this might approach a geometric series. And it turns out that for my line scan result, I don't actually do better because I'm limited by compute. So I actually have to massively upscale this simulation if I want to get these values to be even closer to see a true geometric series here. Um, but I'll mention just because I'm proud of it that even on conventional hardware, getting two doublings is pretty hard to do. It's almost impossible to find these experimentally in systems that implement chaotic systems. But it's cool that we can start to see a little bit of this self-similarity pop up here. Okay, so that's the line scan. And it has a runtime that scales the number of values of R that we check, which is why I can't get any more accurately than just checking those two values. Okay. So maybe to put this framing a little bit more precise, and there's this whole lecture slide handout that's on the syllabus that really gets into this. And if you want to do these programming interviews, I think that write-up is a really good place to start learning about the lore of this. But oftentimes when we talk about algorithms, we use something called big O notation. So big O notation refers to the leading order term in the scaling of that algorithm's runtime or memory. So an algorithm has a lot of different dependencies on its input size, but big O just refers to whatever dominates as n goes to infinity. So it's like the asymptotic complexity of an algorithm. So for my logistic map line search, the n here would correspond to the number of R values that I check, because the runtime of my algorithm is fundamentally limited by how many of those I'm willing to check and how much compute I'm willing to burn there. And you'll recall that affects the precision of my estimates, which ultimately determines why I am bounded by how accurate I can get here. Okay, so I would say that my line scan has a runtime complexity of order n, meaning that it's linear in the size of its input. So if I double the number of values of R that I check, I'd say that I doubled the runtime to leading order. And I keep saying to leading order because you can imagine, in Python, like in all other languages, whenever I run anything, there might be a constant term like the time to allocate memory or to start up the interpreter, et cetera, et cetera. But as n gets very large, that term gets washed out by whatever that linear scaling is. So again, it's always the asymptotic regime. It's never the sublinear regime. Okay, so the line search has a complexity of order n. Other common runtimes that you'll see pop up are constant runtime. So for example, getting the first element from a list always takes the same amount of time regardless of the list length. So that's constant runtime. Just evaluating a cell in an IPython notebook and getting that started has a constant runtime. So certain operations that don't require looking at everything will have constant runtime. So that's a very common one. And then sometimes you'll see cases of algorithms that have polynomial runtimes. So they might check every element in an array twice, so they'll have n squared runtime. And the distance matrix calculation that we saw in the last class is a classic example of something that has n squared runtime, because finding pairwise distances requires you to look up every distance twice. So polynomial runtimes are super common. And then not so much in this class, but definitely out in computer science land, you'll often see factors that scale with log n. And we're going to see one example of that today. But as a rule of thumb, a lot of these big O notation problems are some amalgamy of constant, polynomial, or log n. Sometimes products of these, you might have n log n or something, but you can usually suss it out just by feeling out which parts of the algorithm limit the time. So if you want a bunch of examples of this, I'd encourage you to look through these MIT notes. A lot of cases where this comes up is sorting. So sorting an array can be done in n log n as its fastest time, for example. But there's a lot of other like classic algorithms that have very famous minimal scalings. So whenever you hear me say that something is n squared, I'm really referring to asymptotically, if its input gets really big, how do I expect its runtime to scale? Okay. And just like you can do this for runtime, you can also do this for memory. So how much do I have to store? For the logistic map, I have to store solutions for every single value of R. So I'd say they also have linear memory requirements for that because I'm storing every single value in my array. Okay. So I just did a line scan where I searched an array by basically looking at every single element. But the faster way to do this operation is by doing something called a binary search. And some of you guys might have seen this before in different contexts, but we're going to go through this because the way we're going to use this for the logistic map is actually a little bit less trivial than you might think. So the idea here is really simple, which is that if I'm trying to find something like a value in an array, uh, if the array is sorted, then I don't actually have to look at every element, right? So because it's only when I look at every single element in an array that I'm going to have order and runtime because I have to touch every single thing once. But if it's sorted and I'm just trying to, for example, find where an element goes in the array or where I can look up an element, then I really only have to look at half of the array at each time, right? So at the first point, I just see whether my lookup index is greater than or equal to the middle of the array. Depending on whether it's greater than or equal to, here was less than. I then can say that I know it's not in this first half. Then I can take that subarray, and then I can sort of keep having the size of the array. And so basically, if I can skip looking at a large fraction of the elements because my elements are sorted, that's a giveaway that maybe you can do better than linear scaling in your runtime. And this is a canonical example of a problem that can be done this way. But there are a lot of more subtle cases where it turns out you don't actually have to look at all of your elements. And in physics, we often are working with problems that are defined on a lattice, right? You have a spatial coordinate, or maybe you have time. And so they often will have this structure where you implicitly have sorting present, maybe because your time points are in order or because your lattice coordinates have space associated with them. And so that's going to be behind a lot of speed ups because it allows you to do quick lookups that don't look at the entire domain. The famous example of this is in n body simulations, there's ways to avoid doing a full n squared pairwise lookups just by sorting your elements in your lattice and stuff like that. Okay, so this is binary search. So, this is the diagram, but I think my code is probably an easier way to think about this. So the idea is I want to find the index where some value would go if I were to insert this value into the array. So here I'm trying to insert, and I keep looking up to find where it goes. And the way that I'm going to implement this, there's a lot of different ways of doing this, is using what's called a two-pointer. So the idea is that I'm going to initialize two indices. One points to the front of the array, one points to the back. So if I have 5 elements, this is going to be element 0. This is going to be index 4, but it's the 5th element because we start at 0. And in order to avoid looking at the entire array, I'm going to assume my array is sorted. I'm going to start my indices at the front of the bottom, or my pointers at the front and the back. And then until my 2 pointers collide, I'm going to, at every iteration of this while loop, find the midpoint of my 2 pointers. This double division symbol allows you to find the middle rounded to the nearest integer, so I don't have to worry about any casting. I'm then going to compare the middle element to the value I'm trying to insert. And depending on whether my target value is greater than the middle point or it's less than the middle point, I'll update either my bottom pointer to be the current middle element or vice versa. And this will keep running until those 2 pointers have narrowed and squeezed in on a single interval. So this is basically a one-to-one implementation of this thing where the yellow corresponds to what's between the pointers. So at each step, I sort of have the array, or I decimate it by reducing the amount of space between the 2 pointers.
Is there any way to parallelize any sort of testing pipeline?
To parallelize what?
Yeah, because you're only using like one CPU, but is there like a way to split up the task? Like as if you have multiple computers?
I think that so you could definitely vectorize this if I was, for example, doing it across like multiple independent dimensions. So I was trying to do like a lookup on each element of a vector. But here I don't think there's any intrinsic speed up you can get or any vectorization you can get here.
I mean in general. Like if you just had a function that was like unique to your thing, but like it's possible for that like one value of the function is dependent on another. And you just want to have a whole plot so you like write it all at once.
The short answer is no. Python has the same public global interpreter lock that actually prevents it from spawning other threads. But the long answer is that there are things to do level to processing, but they're a bit more complicated. But the reference implementation in Python is not level to processing.
But importantly, the algorithmic complexity, so the fundamental like asymptotic runtime and hardware independent is always the same for this algorithm. There might be specificities that are programming language dependent, but the fundamental runtime is sort of like a mathematical invariant of this algorithm, which is kind of cool. Okay, so we can, I probably won't run this because it takes apparently 41 seconds to run. But so this is me running binary search on an array that looks like it has about 10 elements in it, and it does it, and this method works. So what I'm going to do is I'm going to run a timing test. And I ran these before class because they take too long. But basically, I'm going to take these big arrays and I'm going to make this array bigger and bigger because the length of this array basically corresponds to the n for this problem. And so we're going to see what the scaling of the runtime of my binary search implementation is as I make this array longer and longer. So all this code is just me running my timing test where I'm going to pick an n. N is going to start very, very small, and it's going to get, I guess I went up to 5,000. And I'm just going to rerun my code and see how long it takes. And I'm going to do 10,000 replicates at each point. Okay, so when I do that runtime test, I get this kind of interesting pattern, which is that the runtime, is pretty fast, but importantly, you can see it looks like it's starting to saturate. And it's not going to truly saturate, but it certainly is growing slower than linear. And this is the magic of algorithms like binary search, which is that because they don't touch every element in the array, they can actually run faster than linear. So this is an example of an algorithm that has a runtime that is log of n. So it's growing, but it's growing slower than a straight line. And this is really cool because this is the key to a lot of famous algorithms. Is anything that converts a factor of n to a factor of log n is like a way to become famous, basically. And so this is a kind of the canonical example. And the intuition here is, again, the fact that I had n elements, but I didn't have to actually touch every single one of them. And so there was a way to shave off having to do stuff because I had a sorted array. Okay, so this is an example of a log n algorithm. We'll see a couple of these go by. Fourier transforms famously, there's a n log n algorithm for them, so that's really fast. But a lot of famous things are basically involved finding a way to do something that looks a lot like that binary search operation where you can only look at part of the array at once. Okay, so that's log n, and that's a very nice thing to be able to do, and that's a lot of good algorithms do that. Okay, so what I'm going to do is I'm going to modify my period doubling calculation to, instead of going and exhaustively searching every single one of these values, I'm going to instead use binary search to try to narrow in on each of these bifurcation points. And my code is actually, it ended up being a lot more involved than I thought it was going to be. So I might not get into the nitty gritty of each line because it's kind of a lot. But the basic idea is that compared to my vanilla binary search, I have a couple of additional complicating factors when I have the logistic map. The biggest one is that my condition isn't, whether I'm less than or equal to. Really, my condition is I have a pointer. Is the trajectory of that pointer period 1 or period 2 or period 4? So I need to have a pointer that computes the period of the trajectory here, a pointer that computes the period here, and then my midpoint, I have to evaluate that. And you need to see if the doubling happened before or after. So I'm going to still use this idea of checking each side, but that actual calculation is going to be a lot trickier than doing a comparison or something.
Clarify the period thing.
Yeah, so at each of these points, like this is r equals 2.9. If I were to simulate the logistic map for like 1,000 time points, this is just telling me that all of those time points would just go to 0.65 or something. So it's like imagine I'm like looking at the entire solution at that point. I'm just not plotting it versus time. I'm just taking all of those time points and smashing them together on the same point on the plot. I sometimes think of it as like, if I have my plot of my trajectory, I sort of like turn it on its side and look down it or something. And that's kind of what's happening here. So if it goes to a fixed point, the trajectory looks like a line. So I like turn it and it looks like a line when I stare it down. And so if it's like oscillating, then that means that like at r equals 3.1, it's going back and forth. So I turn it and I just see two values or something. At least that's how I visualize it. But you should think of like every single vertical slice is an entire trajectory. Yeah, bifurcation diagrams are they're their own genre of sort of of interpretation, and they really only pop up in nonlinear dynamics like this. Okay, so my logistic map bifurcation detector, it's going to symbolically try to figure out if I have a pointer here, what the period is, if I have a pointer halfway between, what the period is, and if I have a pointer over here, what the period is. That's what's going to have to do is this three-way comparison in order to decide which pointer to update. So I have an implementation of that that's very similar to what I was doing before for the line scan. It just structures the problem a little bit differently to tell me which interval to use, but it's very similar to ahead. I won't get into the details, but the basic idea is doing the same comparison I did just with 3 pointers. And then my algorithm for actually finding these points is actually going to look very similar to the binary search algorithm, which is I'm going to initialize a gap. I'm going to update the pointer to point to the middle. I'm going to check those 3 values, and then depending on where the bifurcation happened, it's going to narrow down. So this is basically almost identical to binary search. It just has a little bit of extra steps because we're doing this with a lot more sophisticated system. Okay, so this code, it might be worth reviewing if you're interested in pointers and binary search and stuff. One subtlety I'll point out is that technically I don't have a single value I'm looking up, right? Because really I want to get this value and that value and that value, et cetera, et cetera. So I'm actually doing a multiple root find, which is a famous problem in numerical recipes. So I'm actually going to seed a bunch of sub-problems that start at different points and try to find the nearest bifurcation. Okay, and the hope is that by doing it this way, I'm going to be able to save a little bit of compute compared to just checking every value of R. And maybe that's going to allow me to get to slightly higher precision rather than checking every single value of R manually. Okay, so, I have my code that implements this. And I ran it. I won't rerun it because I don't know if I have it in my memory. Actually, I think I do have it in my memory. Oh yeah, okay, cool. Okay, so this is me plotting the gaps between successive bifurcations found by this optimized binary search space bifurcation finder. So this is again finding the equivalent of the gap between this interval to this interval to this interval. I'm just using the values returned by my optimized code now. So I'm still plotting the gap between successive bifurcations. Okay, so I take those gaps, and if I find their ratio of them to each other, I start to see that at least the first 2 gaps are almost the same number now. So it's about 4.67. And this one starts to get a little bit off, so I start losing precision there. So this suggests that at least the first 2 period doublings, so when I go from here to here and then to here, decreased by a constant geometric ratio, which is about 4.67. And if I had a lot higher precision, I would see a bunch more even smaller bifurcations, all of which would have that gap decreasing by 4.67 each time. It's just that that is a geometric series that gets really, really tiny, really, really fast. So that number 4.667, 669, I should get that right. This is called the Feigenbaum constant. And this pops up in all sorts of weird systems where you wouldn't expect it to pop up. It's basically a universal property of a lot of different physical systems as they undergo the transition to chaotic regimes. So here I'm using the logistic map because this is basically the simplest system that shows this. But for example, there are turbulent systems where as you increase the driving, you'll see these very stereotyped doublings of the amount of vorticity until eventually turbulence breaks out. And this exact same number pops up in the ratio of those bifurcations. So this is one of the really famous results in chaos because it was such a crazy thing when they found it. And it turned out that a lot of finding this involved really, really fancy numerics to actually prove that this number was constant in real systems. And I'll just mention that I've never been able to find it. I don't think I've ever found a tutorial that managed to get the Feigenbaum constant up to two doublings. It's actually pretty hard to do. So this binary search code is actually doing some really heavy lifting here. This would actually be pretty hard to get off of a normal bifurcation diagram. So this, I don't know, I think this is cool. Yeah. Anyways, that's the Feigenbaum constant enabled using just the fact that we were able to find this log n binary search algorithm. Okay. So then the other thing I wanted to talk about, and this actually doesn't come up in the homework, it's just something that I think is kind of interesting, is that a lot of the times when you're trying to come up with a faster way of doing an algorithm, the fastest algorithms are ones that or the most sort of like famous numerical recipes are those where you manage to take a difficult problem and split it up using a method like recursion. So recursion is not on the homework, but I think it's worth knowing about. But the idea is that if I have some algorithm that has a structure where I can write the next state of the output as a function of its previous structures, this is an inductive structure. There often are ways to accelerate that to speed up the runtime. So for example, something like the logistic map updates the next value based off of its previous value. And so you can actually do various methods to sort of speed that up. So I don't have time to get into all this code. It's kind of very tutorially because it's not getting into anything interesting. But I encourage you, if you're interested in learning a little bit about speed ups and dynamic programming, to check this out, especially if you haven't seen this before. One thing I do want to talk about, because I don't think it's covered in a lot of algorithms textbooks, is that you can actually think about recursion versus dynamic programming as dynamical systems. So if I have an algorithm like logistic map where I increment it by taking the previous value, running some operation, getting the new value, that corresponds to sort of a backwards to forwards traversal of the set of values. That technically corresponds to dynamic programming in an algorithms textbook. Conversely, a lot of problems that are solved using recursion, which involve taking sort of the next value and sort of updating continuously until you hit a base case, a lot of those you can actually think of traversing a dynamical system backwards. So there's a very nice structure to recursion versus dynamic programming in terms of dynamical systems, where basically is whether you're simulating from an initial condition forward or whether you're starting at the end and working your way back. And this can be sort of an interesting alternative way of thinking about some of these algorithms. Okay, and yeah, and just recursion we'll talk about a little bit more in context of Fourier transforms, but if you've never seen recursion in one of the intro classes, I'd encourage you to maybe just take a look at some of my examples just to see how it works, because it's a little bit weird, but once you get used to it, it's pretty recognizable. Okay, so I'll go ahead and wrap up there, and we'll talk about Fourier transforms on Monday. All right, thanks.